So today I'm going to talk about the level cirrhosis machine learning model. Um, so liver cirrhosis is a disease that requires early detection and accurate classification to improve patient outcomes. So in this model, it aims to build a machine learning model to classify the stage of cirrhosis based on clinical and the laboratory data. And this is the data dictionary. And let us start with preprocessing part is here, and for handling missing values. Uh, so medical data sets often have incomplete reports due to missing values, also incomplete patient histories. So to handling those missing values, we just simply replace this data to zeros, and for the feature engineering, we just transform the stage variable from a multi-class label like 1 to 4 to a binary classification problem, which stage 4 means cirrhosis is present, and stage 1, 2, 3 is to 0, which is no cirrhosis. So basically, this transformation allows us models to focus on distinguishing severe cases from non-severe ones. And we addressed the skewness and the outliers here. Of like to normalize these distributions, we apply like log transformation, reducing extreme variance and improved model generation to detect and for outliers to detect and handle outliers. We used Takis rule, basically identifying extreme values based on interquartile range. And once we detected, we applied internalization, capping extreme values to prevent them from distorting the model training process. And by collecting the skewness and outliers, we improve data stability and minimize the bias in our models. And for encoding categorical variables, like since machine learning models operate on like numerical data, we just need to convert it categorical variables into numerical representations using like one-hot encoding. For example, drug type and sex, like male versus female. And for the correlation heat map is used to do feature selection and correlation analysis. It is to improve like model efficiency if we use the most relevant features based on correlation analysis, like analyze the features dependencies and maybe remove redundant variables is to minimizing the collinear tree and ensuring stable model learning. So this is the and comes to model selection and training. We apply like maybe two approaches for the model selection. The first one is traditional approach, which is manually selected decision tree classifier pipeline here. So to build like a baseline model, we implemented a decision tree classifier. This to we did feature standardization, which is like z-score normalization to improve numerical stability and synthetic minority or sampling technique. It's to balance in the dataset and prevent bias towards majority class. And the outcome here is like holdout sample test accuracy is 9% and the cross validation score is 67.2. Like this decision tree model provides a simple interpretation approach, but it tends to overfit the training data as like lower test accuracy compared to cross-validation scores. And we used pi caret local classifier here So it is like a automated machine learning library. It is to compare multiple classifiers like best performing model. Here we detected uh top performing models from this pie. Like the first one, like the best performing one is extra trees classifier. It has achieved like accuracy of 75.77% while maintaining like a balanced recall and with F1 score here. And for logistic regression, it has a like highest AUC and suggesting a good separation between class. But it performed worse on recall. For light GBM perform like it performed best on recall, making like 60, which is a 64%, making it a good option to reduce the false negatives in medical diagnosis. For why these models treat this data set, like decision trees and random forest, it work well with like imbalanced data sets. And also can handle nonlinear relationships. And also it provides feature importance rankings, which are useful for medical interpretability. And for extra tree classifier, it performs well when features have correlations, which exist in this dataset. And it works efficiently with a moderate size dataset. And for the light GBM, it is efficient and faster, and it has a high recall in this case. And for logistic regression, it has a high AUC. It's just a strong ability to distinguish between positive and negative cases, and it works well if the data set follows linear decision boundary. And for some insights and real-world implications, so extra tree and random forest have a relative high accuracy in this case, and making them like has a great general performance. And for light GBM and logistic question, it has a high recall, meaning they are less likely to miss actual cirrhosis cases, which is crucial in medical context. And for decision trees and random forest, there it tends to overfit. Maybe like they may not generalize well on like unseen data. And for regression, for logistic regression, it has lower variance, but it assumes linear relationships which might not fully capture disease progressions. And in order to reducing false negatives, high recall models like IGBM, it can ensure fewer cirrhosis cases go undetected, improving like early intervention. And for the feature importance analysis, it helps doctor prioritize lab tests based on their contributions to classification. That's it.